Hello everyone. In this video, we'll take a look at some basic concepts of graph theory. Now, what do we mean by a graph in computer science, especially in graph theory as a part of discrete maths or as a part of data structures? In your school days, you must have plotted graphs which have x and y axis, just like this one. X may indicate one quantity like time and y may indicate another quantity. Okay, so for example, y may denote the speed of an object and x may denote the time. Okay, so these are not the kind of graphs that we are concerned about in graph theory or discrete structures or data structures. We are interested in these types of graphs. Okay, so here our graphs contain certain points or circles which we call as nodes or vertices, and connecting these vertices, these lines are called as edges or arcs. So let's take a look at a formal mathematical definition of graph. So a graph G is a tuple V comma E. Whenever we draw parenthesis and we write V comma E, that means this order must be followed. So first there is a set of vertices and E is the set of edges. Okay. Now V has to be a non-empty set. So in a graph, it can be possible that there are some vertices, but there are no edges connecting those vertices. Such a graph will be called as an empty graph or null graph. Okay, but vertices should be there. So V has to be a non-empty set. Each edge is a pair of vertices V comma W, where V and W belong to capital V. Okay, so let's say there is an edge between the vertices V and W. Now there is no order between V and W. You can call the same edge as VW and you can call it as WV as well. Okay, so that's why the set notation is used here, curly brackets. In a set, order of elements doesn't matter. So we have just used curly brackets to indicate set, meaning that V and W are being connected by this edge. Now V and W, which are connected by this edge, are said to be adjacent to each other. Okay, so let's take a look at some examples. Okay, so now this graph, now what may this graph indicate? Okay, so a graph like this could be used to model a real life situation. Okay, so for example, a graph could represent a road system. Okay, so V1, V2 up to V5, these are the five cities, and the edges E1 to E6 are the roads connecting these cities. Or you can say V1, V2, V3, these can be certain routers, and even up to E6 can be the links between the routers in a computer network, in a local area network. Now, for example, we could also indicate something more abstract, like for example, vertices could be teams. Okay, so V1 is a team, V2, so V1 up to V5 are five teams. And whenever there is an edge joining the vertices, that means so E1 indicates a match was played between V1 and V2. E2 indicates a match was played between V2 and V3. Okay, so edges indicate matches. Okay, so there can be something more abstract like this. Okay, so V1 up to V5 can indicate teams, and a presence of an edge means a match has been played. So you can call it as a tournament graph. Okay, so this is what we mean by that. Okay, now in this case, set of vertices are V1 up to V5 and set of edges are E1, E2 up to E6. Okay. Now, edges incident to vertices. An edge is said to be incident to the vertices to which it is attached. So each of those vertices is said to be an endpoint of that edge. So for example, in this graph, if we take the edge E1, E1 is incident to the vertices V1 and V2, or in other words, you can say V1 and V2 are the endpoints of the edge E1. Okay, so we are in a position now to refine the definition of a graph. Earlier, we simply defined a graph as an ordered pair of vertices and edges. We defined G equal to, in parenthesis, V comma E. So whatever we write in parenthesis normally is an ordered pair. Okay, so if our vertices are just vertex labels, and if our edge set is also just edge labels, without having the pictorial representation of the graph, we cannot understand how exactly the graph is or how it looks. So to completely describe a graph, we also need to understand which edge has which vertices as its endpoint. Okay, so to describe where the edges go, we create a function mapping from the set of edges to an unordered or an ordered pair of vertices. It will be unordered if it is an undirected graph, and it will be an ordered pair of vertices if it's a directed graph. So this function from E to V cross B is called incidence function psi. V cross B because it will be a pair of vertices. Okay, so we'll take cross product for pair of vertices. In some cases, the edge set E is directly used to indicate the incidence function instead of naming the edges separately. That is, instead of having an edge set which describes just the labels of the edges, we simply represent that edge with its endpoints directly. Okay, so first let's take a look at the example of a graph. Vertex set is simple. Here there are 5 vertices A, B, C, D, and E. Edge set is also simple. We are simply writing the labels of the edges, which are E1, E2, E3, E4 up to E8. Now, incidence function will be a mapping. So psi will be a mapping from a particular edge to unordered or ordered pair of vertices. Now, because this is an undirected graph, there will be unordered pair of vertices. That is a set of vertices. Okay, the pair will be within curly brackets. Okay, so E1 is between A and B, E2 is between B and C, E3 is between C and C, self loop, so on and so forth up to E8. Now let's take an example of this graph. Okay, so graph G is equal to V comma E with V equal to 1, 2, 3, 4, 5. And now here we have directly mentioned the edge set as unordered pairs. So instead of having separate edge set as just the labels between the or labels of the edges and then having an incidence function, our edge set here itself serves as an incidence function. Now in the previous graph, we saw a case where an edge started and ended at the same vertex. That is, the edge started at vertex C and ended at vertex C itself. So if an edge has only one endpoint, it is called as a loop edge or it is called as a self loop to avoid confusion with the electric loops. Because graphs can also be used to denote electric networks and loop has a different meaning in electrical networks. So sometimes it is also called as self loop. If two or more edges have the same endpoints, then they are called as multiple or parallel edges. So in this case, D has a self loop and there are parallel edges between the vertices B and C. A graph that does not have loops or multiple or parallel edges is called as a simple graph. The degree of a vertex V is the number of edges. Okay, so this is the next important term. What do you mean by degree? Okay, so we calculate degree for a vertex. So degree of a vertex V is the number of edges incident to that vertex. That means number of edges that has this particular vertex as one of the endpoints. Okay, it is denoted by DEG of V. A loop at a vertex contributes twice to the degree of that vertex. thing which is obvious because there are two connections effectively. That same vertex is effectively both the endpoints of that edge in case of a self loop. So it contributes twice. Now let's try to calculate the degrees for all the vertices in this graph. Let's say for vertex A, there are two edges, AB and AF. So the degree will be 2. For vertex B, there are edges BA, BF, BE and BC. So the degree should be 4. For vertex C, we have CB, CF, CE and CD. So degree will again be 4. For vertex D, we only have one edge, that is DC. Therefore, degree will be 1. There is a special terminology for such a vertex. It is called as a pendant vertex. If the degree is 1, it is called as a pendant vertex. Next, we have the vertex E. In case of E, we have the edge EF, EB, and EC. So it is 3. In case of F, we have FA, FB, FC, and FE. So degree is 4. In case of G, as you can see, there are no connecting edges. This is allowed. Okay. This is still a part of the graph. G is still a part of the graph. Okay. But it does not have any edges connecting it with the rest of the graph. It is disconnected. And it makes the entire graph disconnected as well. So what is such a vertex called? There is also another terminology, like D is called as a pendant vertex. A vertex with degree 0 is called as an isolated vertex. So it has degree 0. Let's take a look at another example. Now we have multiple edges or parallel edges and self loops. So for A, it will be 1, 2, 3, 4. For B, it will be 1, 2, 3, 4. And for the self loop, will count twice, so 6. For C, it will be 1. For D, it will be 1, 2, 3, 4, 5. For E, it will be 1, 2, 3, 4, 5, 6. Okay, so these are the degrees. Okay, now there is an interesting result for graphs, which is a simple observation also. It is called as a handshaking lemma. In any graph, the sum of the degrees of all the vertices equals twice the number of edges. Now, each edge, if you consider, is contributing 1 degree count, like 1 degree count to each of its endpoints, right? So, therefore, the total degree count will be twice the number of edges. Okay. So mathematically, we can write this as summation of all the degrees is equal to twice the number of edges. Now, why is it called so? Okay. Now, let's say in this graph, the vertices represent people. Okay. And we draw an edge between the vertices whenever the corresponding people have shaken hands. So, for example, John and Joan have shaken hands, John and Jean have shaken hands, but John and Jill has not shaken. They have not shaken their hands. They did not have a handshake. So there is no edge between John and Jill. Okay. So now with this interpretation, the number of edges represents the total number of handshakes. The degree of a vertex is the number of hands. So for example, degree of John means John has shaken hands with 2 people. So number of hands shaken by the corresponding person. John has shaken 2 hands, one of Joan and one of Jean. So sum of the degrees is the total number of hands shaken. Total number of handshakes that took place, total number of hands shaken. Sum of the degrees is total number of hands shaken. That is, handshaking lemma states that total number of hands shaken will be twice the number of handshakes, which is like a common sense because every time there is a handshake, the handshake count of John also increases and handshake count of Joan also increases. For example, if we count for this particular handshake phenomena, handshake count of John will also increase and handshake count of John will also increase if we count for this particular handshake taking place. If we count for this particular handshake taking place, count of John is also going to increase and count of Jean is also going to increase, right? So that is where the name kind of originates from. Now some mathematical applications of this. Okay. Now, if we know that a graph has 10 vertices, and if we also know that the degree of each vertex is 6, we know that. Okay. We want to count how many edges are there in a graph. So we can do that with the handshaking lemma. So total number of, or the total sum of degrees. Total sum of degrees will be 10 vertices multiplied by each with a degree of 6. So that is 60. And it is equal to twice the number of edges. So therefore number of edges will be 30. Next, if a graph has 5 vertices, can each vertex have a degree 3? So if I say there are 5 vertices, each of degree 3, is it possible? Let's take a look mathematically, purely mathematically. Okay. So sum of the degrees will be 5 into 3, that is 15. And 15 cannot be twice the number of edges. So if we say total number of edges, if we substitute that in handshaking lemma, total number of edges will be 7.5. So which is not possible, right? So it is not possible that if your graph has odd number of vertices and all of them have odd degree, then they cannot be a graph. It is not possible. Okay. So we can state this as a result. So in any graph, number of vertices with odd degree is even. Okay. So in the example, the number of vertices were 5. Degree of each vertex was 3. That was not possible. But we could have 4 vertices with degree 3. That could have been possible. So we can have odd degree, that is 3, for even number of vertices, that is, let's say 4 vertices. So 4 vertices could have degree 3. Okay. So that could have been possible. Now, why this is so? Because obviously, uh, this particular quantity, if we divide it by 2, it should be a whole number. And this is only possible if this particular quantity is even. Okay. Now, the left-hand side of this equation can be split into two terms. Sum taken over the set V odd of vertices with odd degree and sum taken over the set V even of vertices with even degree. Okay, if we divide the vertices of the graph into two sets V odd and V even, and then we take the sum of their respective degrees, this is anyways going to be even because these are all the vertices with even degree. So the sum of those degrees is anyways going to be even. Okay, so RHS is even, on LHS this quantity is even. Only thing left is this quantity should be even. Now for this quantity to be even, your number of vertices should be even. So odd number multiplied by even number gives you an even number, right? Odd number multiplied by odd number gives you odd number. So this the number of vertices in V odd has to be even. Now, a very dummy kind of an example, let's say a very simple example, which kind of simulates or tries to model a real world situation. Let's say you are starting a new social network application. You are starting a new social network, let's say. Okay, and okay, so so in a social network, each vertex represents a user, and a connection between the users is represented by H. It is a mutual connection. Okay, so like LinkedIn, if A adds B to his or her network, then A and B are connected to each other. Or in Facebook, if A accepts the friend request of B, then A and B are friends. It is equal. Okay. It is not like Instagram follow relation where A follows B So then it will have a direction. A follows B. B does not follow, B necessarily may not follow A. A follows B. So that is not the case here. Here we have a connection that is symmetric, we can say. Okay, so when A and B are connected, it looks both, like it looks same from both sides. A is connected to B, B is connected to A. Now, on an average, you have estimated that each user will have on an average, let's say 300 connections. Now, you want to estimate how many users should register to your platform so that the total connection count becomes 1 million. Okay, and just an estimate because 300 connections on an average. Some may have less, some may have more. So you want an estimate. What is the minimum number of users required to achieve 1 million connections on your platform? So if you apply handshaking lemma, the edges, edges are your 1 million connections and vertices are the users. So that is X, that is what we want to find out. And degree for each of them is 300. So 300x equal to twice the number of edges. So 300 into V is equal to twice the number of edges. And then number of vertices will be 2 million divided by 300, roughly 6,667. So approximately when 6,667 users will register on your social media platform, then there is a possibility of having 1 million connections. Okay, now let's move on to directed graphs. The intuition is just like I told you. So let's say uh, it's an Instagram kind of a social media we are trying to model over here, where B follows A. Okay, so we draw an arrow from B to A. C follows A, so there is an arrow from C to A. B follows D, there is an arrow from B to D. A follows D, there is an arrow from A to D. Now, as you can see, there is some significance to this direction. Okay, you cannot say that the edge is AB. No, the edge is BA. From B to A, from C to A. So you can say it in only one way. And therefore, our definition will also have a slight change. Again, G is again a pair of V and E. No change there. V is a set of vertices. That is also the same. E is a set of n edges. Okay, E is a set of edges. That is also fine. Edges are also called arcs. Vertices are also called nodes. That is also fine. Now, each edge now is an ordered pair. And when you have an ordered pair, which you also called as a tuple, for an ordered pair with two elements, we call it as a tuple. Oh, sorry. So in this case, it's an ordered pair because there are two elements, we call it as a pair. Okay. So it's a tuple with two elements, that is V and W. It's an ordered pair. That means the edge starts from V and it goes to W. V is the from vertex and W is the to vertex. In this graph, if we want to depict this graph using this notation, so we'll draw it as AD because it is from A to D, from B to A, from B to D, and from C to A. Next concept is degree of vertices in a directed graph. Okay, so out degree of a vertex, outward pointing normal positive. So out degree of a vertex, that's why the convention is followed here again. Dig plus of V. Out degree is denoted by degree plus of V. That means all the edges which are outgoing from V. V is the starting point. All the edges for which V is the starting point. That count is called as the out degree. And if you count the edges which are coming towards V, that count will be called as the in degree of that vertex or degree minus. Each loop contributes 1 to both the in degree and out degree count. I think it is obvious because it is both outgoing as well as incoming towards the vertex. Let's take a look at the example for the calculations. So from U to V, therefore it is an outgoing edge. So out degree count will be 1. There is no incoming edge at U. So in degree will be 0. For V, there is only one incoming edge. There are three outgoing edges. So in degree 1, out degree 3. For W, one incoming edge, two outgoing edges, and I think you get the point. Okay, so this is how you can calculate. Again, we have an isolated vertex here, and we can say U is a pendant vertex. Now, the handshaking lemma version for digraphs, instead of taking the uh, sum of the degrees of all the vertices, what we can do is we can take the sum of all the in degrees and sum of all the out degrees. That sum is equal. Okay, so there are as many incoming edges as there are outgoing edges. And if you take the sum of this will be twice the number of edges. So handshaking lemma for undirected was taking the sum of all degrees, it is equal to twice the number of edges. Now here you imagine this is equal to mod E, that is, this is equal to the number of edges in E. This is equal to number of edges in E. So if you add these two things up, it will be twice E. Okay. So example. In this case, if we want to verify the handshaking lemma, let's first calculate all the in degrees. I think that calculation is clear. So these are all in degrees. In degree of A is 2. For example, we'll just verify for one vertex. Why is it 2? This is 2 because one from this incoming edge and one because of the self loop. Degree of B, there are two incoming edges at B and so on. Okay, so all in degrees. If we calculate the sum, okay, now we'll take the sum of all these. So 2 plus 2, 4 plus 3, 7 plus 2, 9 plus 3, 12. Sum of all in degrees is 12. For out degrees, out degree of A, one outgoing edge, two outgoing edge, third outgoing edge, and the fourth one is this because of the self loop. For B, there is only one outgoing edge, and so on. Okay. So 4 plus 1, 5 plus 2, 7 plus 2, 9 plus 3, 12. Verified. So sum of the in degrees is equal to sum of the out degrees, and if you count the number of edges, you have one. Okay, I'll start from here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So there are 12 edges as well. Verified. Okay. Now again, the two types of edges that we had discussed before, that is loops and multiple edges, are also applicable here. But only additional thing here is that the multiple edges connecting both the vertices, they should be in the same direction. Only then we can call them as multiple or parallel edges. If we have an edge from A to B and from B to A, so both of them have opposite directions. They are between the same pair of vertices, but they have opposite directions. Then they will not be called as multiple edges or multiple arcs. An edge joining vertex to itself is again a self loop. Okay, so as you can see from the example, they are in the same direction, then there are multiple arcs or multiple loops. Sorry, multiple arcs or multiple edges. Okay. If they are in opposite direction, then this graph will still be a simple graph. Right now, this graph is not a simple graph because we have two edges going from W to V, and both are in the same direction. If one of them was in opposite direction, then it would have been a simple graph. Okay, this is a self loop. So now there is a certain graph terminology. Okay, so simple graph or simple directed graph, basically you call it simple when there are no multiple edges and no loops. If there are edges, if there are multiple edges allowed, then we call it as a multigraph or directed multigraph, depending on the nature. If it has multiple edges and loops allowed, it is called as a pseudograph. And if there is a mix of directed and undirected edges, and multiple edges and loops are also allowed, then it is called as a mixed graph. But in most scenarios, simple graphs and simple directed graphs. So basically, simple graphs will suffice. Okay. Neighbor. Next terminology that we have is neighbor. Now, neighbor means a vertex U is a neighbor or equivalently adjacent to a vertex V. A vertex U is a neighbor of a vertex V in a graph if there is an edge UV belonging to the set of edges. Like we had seen right towards the first or second slide, if there is an edge between V and W, then V and W were called adjacent. Similarly, here U and V are adjacent, or you can say U and V are neighbors of each other. For a directed graph now, U is an in neighbor. So UV, that means edge is going from U to V. So if you look at V, so imagine that you are standing at V and there is an edge coming to you, something coming towards you from U. So there is an incoming edge. So you can say U is an in neighbor of V because a vertex is coming towards V from U. And it is an out neighbor if the edge is VU. If edge goes from V to U, then U is an out neighbor. Okay. So we also say two edges or arcs are neighbors if they share a vertex. Okay. But normally this terminology is used for neighboring vertices rather than neighboring edges. But still, in some cases, this terminology may also be used, neighboring edges. Okay, neighborhood. Now, set of all vertices which are neighbors of a particular vertex will be called as the neighborhood. Okay, so neighborhood is nothing but a set of all vertices U such that U and V belongs. So U, V are edges. This is simple for undirected. For directed, we have ng plus to indicate set of out neighbors and ng minus to indicate the set of in neighbors. Now, why plus for out and minus for in? This same convention of plus for out and minus for in will be followed for one more definition, one more concept later on in this presentation. So basically, you might have studied the right hand thumb rule. Okay. Basically, so if you consider a plane and if there is a normal to that plane, if that normal is pointing outwards from that plane, it is considered to be a positive normal. Outgoing normal is considered positive, and so that is facing upwards, outgoing normal. It will be considered positive. Whereas if you consider a plane and there is a normal going inside the plane, okay, downward facing inside the plane, it is considered as a negative normal. So that's why plus and minus, that convention is used here. Okay, so we use ngv for a directed graph. Normally we mean out neighbors. The neighborhood of set of vertices is the union of their neighborhoods. Okay, so we take the neighborhood. If in a directed graph, if we want to find out the neighborhood, we'll take the union of both in neighborhood and out neighborhood. In neighbors and out neighbors, set of all of them. So that is neighborhood. Now, another kind of a small point. Okay. Uh, if you include the vertex, it is called as a close neighborhood. And if you don't include the vertex itself in its neighborhood, then it is called as open neighborhood. So open neighborhood means you do not include the vertex itself in the neighborhood. If you include the vertex itself in the neighborhood, it will be called as a closed neighborhood. If any doubts, questions, or suggestions, you can post them in the comments below. Thank you for watching.